Cesar, I mean, first of all, incredible, mate. Absolutely incredible what you've achieved, man. You must be proud, no? You must be happy and proud of yourself.
Yeah, it was a nice accomplishment. There's still work to do, obviously. Now I gotta see next year what my setup is gonna be, so I can continue the project possibly. But yeah, it's been a nice journey and a fun ride. I wasn't expecting so much coverage on the newspapers because I mean the school didn't tell me they were gonna do this, and then it spread like dominoes. So that it was a bit unexpected. But yeah, it was a very fun project.
So the school kind of put it out online, did they?
Yeah. I mean, they were waiting for results day for the A levels, so they could put it like along with the grades and everything.
Yeah. Okay. And so, thanks a lot for taking the call, Cesar. I just wanted to ask a few questions because, everybody seems to be talking about nuclear fusion at the moment, and it's a hot topic. And for you to actually go out there, put this thing together, I commend you massively. And how old are you?
Thank you. 17. When I started the project, I was 16. Now I'm 17. I'll be turning 18 in 5 days.
Happy birthday, mate, in 5 days. Happy birthday.
Thank you.
Mate, I mean, to do that at 17, like, you don't need me to tell you, mate. I mean, I'm blown away, and I'm sure everybody else is. So, so really well done. All right, I want to ask you a few questions, if that's all right. Okay, so you 3D printed this, right? Most of it is stainless steel. I've read all the documentation you put up. The majority is stainless steel, right? So how did you get that 3D printed, and how long did it take?
So I've been using 3D printers for the past 8 years. I have one here beside me in my room, and the one we used up in the college was different. And basically, I needed a way to hold the Raspberry Pi, mainly because of the camera, because I wanted to have a camera on the viewport, especially for the what are they called, the symposiums and the meetings, and when you show it off, so if they're kids, for example, they don't have to get close to the viewport, because a component like that one, if it gets even a scratch, it needs to be thrown away, at least in an industrial environment. Obviously in a setup like that one, you have a bit more of leeway, but still it will compromise the vacuum a lot. So camera was the first thing I got to work on after I got the plasma, and the 3D printed mount really helped. So I just quickly designed that, and I went through 3 different iterations, I think. So I just kept getting measurements and designing it on my CAD software, and they took about, I think, well, it wasn't continuous printing because I had school going on in the meantime, but a day to print like 3 of the parts for the Fusor mount. So I would go to lesson and then wait a couple of hours for one of the pieces to finish printing, and then we'll go back down, load in the new file, and then we'll print. And then that was the mount done. Other 3D printed parts, that was the main application of the 3D printer. The other application was developed later on, and it was on the vent valve. I don't know if you've seen the latest posts on Fusor.net where I talked about this, but I very simply just 3D printed a sort of clamp with holes in it, and then a mount that will keep the stepper motor still. So then the stepper motor will be screwed onto the clamp, and the clamp screwed onto the valve, and then it would rotate the needle valve, and it's sort of a screw. So there's a valve that moves back and forth, and it increases or decreases the cross section of the flow channel.
And the actual hemisphere, was that 3D printed? The stainless steel hemisphere where the plasma is confined?
No. That was spun. It's a technique called metal spinning. So you have a circular plate, and you spin that really fast, and then you have a wedge that can guide the plane and make it spherical, and then you just cut off the end. So ultimately, you start off with like 6 millimeters thickness, and you end up with 4 millimeters. It's not very homogeneous, but it's close enough.
And I think you use Rhino 3D, right? Rhino 3D.
Yes.
Did you get the schematics, or did you completely do this from scratch? I know it's based on another model in terms of, you know, the person that came up with the inertial confinement, electrostatic inertial confinement device. But did you sort of work out the size, the shape, or did you get a schematic from somewhere?
Well, yeah. So fusers just have basically a list of items that you need to arrange in a certain way. So you need like the grid, the two pumps, a bunch of fittings, and then you can have different shapes. The fuser itself is all from scratch. So I designed the entire thing from scratch. We saw a couple of inspirations on Fusor.net, but if you look at their setups, they're mostly either cross fittings. So just literally two tubes, or well, depending on the cross fitting, but there are 2 or 3 tubes all welded together. Then you have the cylindrical one. There's many different shapes and sizes. Not many people do the sphere one because obviously it's a lot more complicated to get spheres machined and everything. But yeah, no, it was all genuine and original. So the dimensions, we were mainly constrained to the ports that we could buy. So on a website from a supplier called Kurje Lesker, is where we got most of the supplies for the ports and the nipples and the tubes. Everything except the rough vacuum was from Kurje Lesker, and they have a set of dimensions. So every flange has a standard dimension. And then we just decided on one, and we used the inner diameter to calculate the diameter of the hemisphere. And then we sent everything off, including the technical drawings, to the Cambridge workshop, and they welded everything together. They machined it. And it was actually very rewarding getting like these very experienced technicians calling my my technical drawings like good technical drawings, because I'm not guessing, I saw that they use these drawings every day. They see 30 at least a day, and for them to compliment mine, it was quite rewarding. Yeah.
And what made you come up with this? I mean, Cesar, you know, you're 17 years old. What made you sort of, first of all, fascinated with fusion? Second, what made you think I'm going to build a nuclear fusion reactor?
Well, I always liked fusion since I studied it in middle school, but it was something I understood quite easily, but it wasn't like my passion. I mainly wanted to work on aerospace engineering, and that's what the degree I'm pointing towards. Although nuclear engineering, obviously, for obvious reasons, is now starting to become quite interesting. And well, the idea of the fuser actually came up one night when I was scrolling through YouTube, and I saw this video of a fuser. Well, a very rudimentary, bad one, but he did mention the name fuser. And so I did a lot more research, and I saw his was a simple acrylic cylinder that could barely reach a plasma state, and it just made the high voltage. It's called the Cockcroft-Van der Waals voltage multiplier, and he made everything by himself. But he was obviously an expert. He's an engineer who works on ionic thrusters most of the time. This YouTube channel, at least, he features most of this stuff.
I think I've seen this guy. Yeah.
Yeah, and yeah, so I just got the idea, and then I went online, so what fusers are, got really interested, and so as an opportunity to combine all the skills I've been refining and fostering up until that point. So like all the electronics, robotics, I saw the chance of using PCB designs and electrical boards, and then obviously the software, the CAD softwares. And it was just an opportunity for me to pull everything together and in sort of a final assessment.
Amazing. And how many hours do you think you spent, right, from researching what to do until actually putting it together?
I really cannot give you not even a rough estimate, but I can tell you that every day my teacher was available, I would spend up until like 7 p.m. in school in the basement working on this. On most weekends, we would go into school for about 5 hours and work either on the fuser or on the trolley. Every time I had free time or a break or a free period in school, I would go down to the basement and either do my homework there or work on the fuser. So one way or another, whenever I had free time, I was either in school, at home, or building the fusor.
Incredible. So probably hundreds and hundreds of hours. Okay.
Yes,
Right.
yes.
So onto a few kind of technical questions. When I've been studying physics, you're always taught that electrostatic, it always seems to me like electromagnetic force is more prevalent, more important, to study than electrostatics. But I'm hearing more and more about electrostatics in terms of propulsion, in terms of ionic thrusters, and obviously in terms of, and static obviously means that it's not moving. So how are you using, electrostatic forces in the fusor?
Yeah, so the grid has a negative high voltage, so you'd usually go for 30 kilovolts for DD reactions, and this current that passes through the fusor basically allows some electrons to be emitted from the grid, inner grid, to the shell of the fusor, which is at 0 volts. So it creates this huge potential well, and these electrons sometimes they collide with air molecules and they knock off an electron from that molecule, ionizing it. And once you ionize it, it becomes positive because it lost the electron, and it gets attracted to and accelerated towards the center. And once you have a lot of these ions accelerating and colliding either with each other, with the grid, or just shooting off to the other side and hitting the shell or recirculating, then you can create this sort of plasma state around the grid. And it's basically just hot gases, ionized gases.
Right, so you said DD, so you're doing deuterium, and obviously in like a tokamak or something, you're using big magnets to hold the plasma in the center. How are you, obviously, inertial confinement, you're spinning it. How are you spinning those DD molecules, those hydrogen isotopes? How are you spinning them in that vacuum?
Yeah, so instead of spinning the plasma, it's more of a linear collision. So you just have, for example, two ions on opposite sides of the chamber, and they get accelerated. And if you're lucky enough, they have enough energy and they actually collide and they fuse together. Other scenarios, they just miss each other. Obviously, we're talking about quantistic levels, so it's all about probabilities. And you have these curves. I don't know if you heard of them, the cross-section curves for fusion. Yeah. So you have, for example, deuterium and tritium, where it has a peak. So then you know more or less what voltage to use. For DD fusion, it flattens out towards the end. So theoretically, the higher the voltage, the better it gets. But then there's obviously limitations for DD fusion. You don't really know what, you have a variety of voltages that you can use. But it's mostly linear. So unlike the tokamak that the plasma goes around, it just shoots off. And if it misses, you then have the ion recirculate. So it loses all of its energy and then gets accelerated all the way backwards. And that's where the inefficiency comes from, because most of the accelerations, the very large fractions of these accelerations don't result in collision events and in fusion events. So you have all of these ions that get accelerated, gain a lot of energy, but then lose all of that energy being decelerated by the same grid that accelerated them before, and then they get accelerated all the way backwards. And this effect is called recirculation.
So are we talking, I think I was looking earlier on, were we talking 10 to the 9, 10 to the 12 per second, approximately the number of DD molecules that are going through? Is that roughly the number, would you say? Like, because I'm trying to understand how many, ions are passing through there linearly in a second.
Well, I wouldn't be able to give you an estimate on that, but the pressures we would be working with, because it's all a balance of putting in deuterium and removing the air, because first you would run the turbo pump and the roughing pump to remove as much air as possible, and then you do different cycles. So it all comes down to the pressure inside the chamber. Usually you would go for 10 at the -9 torr. I think the 12 is what the pump is rated for. So I'd say about 10, -10, -9 is a good estimate on the pressure that I could obtain within the chamber. And then obviously there's a bunch of leaks, which unfortunately do not allow me to go that far and reach the ultimate pressure of the turbomolecular pump, which would be great if I could. But I I wouldn't be able to tell you how many molecules. I would need to do some calculations, you know, with.
Of course. So we're talking deuterium that's coming in as a gas. And are you
Yes.
are you buying the deuterium gas?
So that would be actually quite expensive because you need to put it inside lecture bottles, and most lecture bottles cannot be refilled. So half of your price goes on the lecture bottle, and the other half goes on the deuterium inside the lecture bottle. So what we came up with, and what some people on Fusor.net also do, is buy heavy water and a simple PEM cell that you can find on those car kits that you fill in with the water, and then you have hydrolysis, and you have the car moving around with the motor. And basically what we do is just feed in heavy water instead of normal water, and you get oxygen from one side that is just discarded, and the other side you get deuterium, and then you fill that deuterium in sort of a tank with oil, that which purpose is just to more or less maintain the pressure for small changes of volume, so you don't put the PEM cell under vacuum or over pressure, so because otherwise you break it because it's very fragile. So you have a system of 2 tanks with the oil, and the oil just moves up and down to either reduce or increase the volume, so you have more or less a constant temperature while you feed the deuterium in. And then the deuterium goes inside the needle valve, which is the one with the motor on, and then that goes straight inside the chamber. And the arrangement we have, theoretically, is actually quite good because you have the inlet on the opposite side of the outlet. So theoretically, the ions or the molecules will go through the grid in order to be sucked out the other side.
I love that. Okay, can I ask you a question? You know, how you envisage this in your mind. So, you know, Cesar, you've done an incredible job here, right? So, how do you, in your mind, picture ions, right? We know that they're free electrons that get pulled off of an atom, in this case, a hydrogen atom, and you know, you just mentioned quantized. So we're talking about probabilistic numbers when we're talking about quantum physics. So, how do you picture in your mind? Do you picture like a field or a wave going through your device, or do you picture individual atoms and these electrons being ripped off? What's your brain's way of imagining that? I'd love to know, because you're really at the forefront of this. If you take your age into account and the money you've spent, minimal, you know, you're like one of the best people in the world. If you take all of that into, you know, a mathematical equation, you compare what ITER are spending way over budget, you compare what, you know, everybody else is doing. So, you know, I'd love to know how you picture in your mind these ions.
I mean, it's very hard at this age to understand it, because obviously I just came out of A levels, and from that point of view, you would imagine it more as a classical physics thing and chemistry, where they teach you about the nucleus and you have the electrons. Electron goes away, you have positive, and you just have a nucleus with the electrons and square brackets and a plus on the corner. Then, however, doing this extra research for the Fusor, you get a lot more information from the quantistic mechanics point of view. So you start to imagine the as you mentioned, the ion as a wave, or as a sort of bunch of circles where you get like a blurry circle where you don't really know where the atom is, but you have sort of probabilities around, and you can I don't know, I have a very specific picture in my mind when they explain quantum mechanics, and they show you a picture of like concentric circles, which are very blurry, and they get the color becomes a lot more vibrant in the center and less vibrant outside near the edge of the circle, and more or less this allows you to perceive probabilities on the position of the molecule, the ion.
Okay, and thank you, Esther. It's really good to know how you see it in your head. And in terms of, I think you used 5 kilovolts, right, a power supply, but ideally you want 30 kilovolts. Then we're talking about slight danger of X-rays, that sort of thing. But would you sort of try it with a 30,000 volt supply? And would you, as far as I know, you wouldn't get ignition in a linear. No. You need to have a proper, you know, a tokamak, or we need to do it another way. Is that correct? So what's the end goal with the Fusor that you're using at the moment?
So the Fusor cannot obviously produce energy nor ignition. It's just to get neutrons. So a company gave us a bunch of bubble tubes, which are neutron detectors, and they have a polymer inside, which when in contact, when struck by neutrons, it creates bubbles, and then you like count all the bubbles, you use a factor that they give you, multiply, and you find the neutrons that have passed through the tube. And then the aim is just to put 2 of those around the chamber, run it, and then get neutrons. Once you get neutrons, you can do a bunch of things, such as create medical isotopes. And medical isotopes are very expensive, and they will be very useful, as we have been told, to nuclear research groups to sort of, well, just do experiments with the decay and stuff like that. So the nuclear research group that I've worked between brackets in the Cambridge University, they said that although they do computational stuff, they said that their medical isotopes are extremely interesting and useful for research of these things and to test and benchmark different computational models. And then, well, it's just fun to have a neutron source, I guess.
Very cool.
Silver, and then you have moderators, and it's a very nice way to also understand how fission reactors work, because then in order to irradiate a certain material, you have different cross sections, and then you need the neutron to be maybe slower or faster, and then you have to surround it with moderator. And if you replace the simple silver that you would use, just because silver has a high cross section, with uranium, you would technically have fission. So it's a very nice experiment. But as I said, and as I reply to many comments, both on the articles and on LinkedIn, I didn't do this with the purpose of creating a revolutionary technology that can create energy with nuclear fusion. It was mostly a project just to challenge myself, and the fact that it was then put online and on news articles was just a consequence of it.
Yeah. Well, I really hope, Cesar, you apply your brain. Well, I hope that doesn't sound condescending, but I hope you do try and build something, because if you've learned all this, I'm assuming yourself, self-taught, if you've learned all of this by the age of 17, I hope that you continue, because you're going to be able to push this into nuclear fusion. I actually went to First Light Fusion a couple of months ago, and they're trying to, I had a full tour of their plant, and they're trying to create, nuclear fusion like many people. And, they would love to have somebody, like you. So, okay, on that then, Cesar, with nuclear fission, my thinking lately is that I think there's about 17 MeV, electron volts, is yes, what you get from a fusor. And from fission, you get 100 times that. You get like 200 mega electron volts from each reaction. So my sort of thinking is that the 10% of the world's energy now comes from fission. Is it massively underrated? Because, I think they're called primordial nuclides, uranium-235. We get amazing amounts of energy from that. If you take a kilogram of uranium-235, if you take a kilogram of, hydrogen isotopes, deuterium, you get about the same output power. Now, I know that obviously, fusion's much better in terms of CO2 and everything else.
Yes.
But are we massively underestimating the potential of fission and the fact that we've got it?
Yeah, no, absolutely. I don't know why my Wi-Fi just went out. I'm using my hotspot now on my phone.
Okay.
Well, fission reactors. I think we are underestimating the technology, especially in countries like Italy, where we had the last referendum we had about nuclear energy wasn't successful. Mainly because I would say, out of perception, it's because we're an old country, and not only, nuclear power plants, big power plants would ruin our landscape. That's true, but mainly because we have an old population that lived through Chernobyl, and they have all of these different stereotypes towards nuclear reactors, and they're just scared and they're not well educated. So I think in general we should have a lot more debates and talks about nuclear energy, mainly because some nuclear reactors are capable of producing plutonium grade, weapons grade plutonium.
Yeah.
So
yeah,
that is also a safety concern. Although there are many treaties, non-proliferation treaties around the world, I mean, that sort of material is very dangerous in the wrong hands. I think I've read somewhere that North Korea had a couple of reactors that were producing weapons-grade plutonium, and in order to counter that, NATO or the UN, I don't remember which one, they gave North Korea, in exchange for that reactor, they gave 2 light water reactors, which don't produce perfect weapons-grade plutonium. So there's all of these different tricks that we need to use in order to make it more safer and delegate with other countries in order to, make sure fission power is used correctly. And then I was also reading the INSAG 7 report for Chernobyl, which is the accident report, where they detailed all the reactor components and the incident itself. And Chernobyl in the Soviet Union was using a RBMK reactor, and I mean, the reason why it exploded was purely because of human mistakes.
Yeah.
And purely human mistakes. From the started from the design up until the moment of the accident in the control room. Then there were other accidents such as 3 Mile Island, but again, human error. And then there was Fukushima, but that was unforeseen weather events. So as long as we, as long as we know that fission power can be used to do wrong, and we are able to prevent weapons-grade uranium and plutonium from being produced, and we use it sensibly, then I don't see a problem. And we need to sensibilize the general population about it. That is the main issue. Also, because now there are MNRs, modular nuclear reactors, that are coming to the market, and I personally think those are going to be the interim energy source until we figure out how to get fusion energy.
Very cool. Yeah, I've been looking at the Rolls-Royce modular micro reactor. I don't think it's ready yet. There's loads of videos surfacing online, but I don't think it's ready. But it looks incredible, and that's obviously using fission. I think for me the main problem is if there's a power outage, if there's a national grid. Say there's an EMP strike in a country that takes out the power grid. I think it's going to be very hard to call the plutonium, the rods, and I think that's the most likely area, because the generators would only last a couple of days. But outside of that, to me, I was looking to launch a rocket into space. If you were to use uranium-235, you'd need like next to nothing, to do it. So if we can find a way of making it safe, fission to me, I've got, because it's here, it exists. We've been using it forever, and everybody's so interested in fusion, and I really get it. But actually, fission's pretty darn cool, in my opinion.
Yeah, exactly. Especially from an engineering point of view, it's not very good to say, but the dangers that can arise from fission reactors can actually make it very interesting, especially to engineers. This is not something you would tell the public, but as an engineer, aspiring engineer, like thinking about solving all the different issues and safety concerns is just very exciting.
Cesar, what for you, I know we're going over a little bit, so I'm going to try not to be too long because I really appreciate your time. But what for you is, for your time in the future, do you think is going to be the best help for humanity? Do you think it's going to be putting all your time into fusion? Do you think it's going to be putting all your time into aerospace, building rockets? Because essentially you're going to have to pick one area, right? And if you've just built that, you can most likely build a miniature rocket, I'm assuming, right? With a liquid hydrogen, liquid oxygen, you understand the physics. That's going to be easier. It's been done before. You can actually Rocket Lab are 3D printing rockets. So there's no doubt in my mind, if you put Cesar in charge of a 3D printed rocket factory, you'd be able to do it. So where do you want to put your time?
Well, you raised a lot of good points there, as the rocket fusion and fission. So obviously they all come with pros and cons. If you spend every resource, monetary and temporal resource on fusion, you also need to develop the space transportation, because tritium it's radioactive, so it's decreasing.
Yeah.
It's being depleted here on Earth. So we need to go on the moon to gather it. So if we want fusion reactors to work well, then we need to make sure we have a good supply of tritium. And I think that the moon is our best shot at this. And also investing a lot of research, a lot of money into fusion research also allows you to develop other technologies such as semiconductor technology, laser technology, which can then be applied to other fields. So although it's risky to invest all your money into only one field, I think there is risk, but not as much as people think, because even if you fail to produce a commercial fusion reactor, you still have years and years of development in laser, semiconductor, plasma confinement, in other sorts of materials that you can then use in other fields. So you always get useful research out of it. Meanwhile, for fissions, I think we're nearing the end of the line, in the sense that we have figured out a lot of technologies for fission reactors. There's molten salt reactors, which are now being developed and slowly coming to life. So that and MNRs, I think we're almost done with fission technology. Then it's only only a matter of finely tuning everything, so improving maybe some of the materials you implement in these types of reactor. But ultimately, we know now that you can convert thorium into fissile uranium, and you can use different more advanced materials to build different types of reactors. So we have a lot of experience in that field. Now we have to push everything into fusion and rockets. And once we get that covered, I think we're ready for interplanetary civilization, because that would be a great milestone, one of the most important milestones so far.
Amazing. So you think, okay, end of life of fission almost, because the isotope of hydrogen tritium is really hard to come by, and fusion, by putting your time into fusion, you've got all of these byproducts, sort of second order effects that you're going to be able to create, from rockets to lasers. I get the rockets, I get the lasers. How will fusion help semiconductors? What will be the key there?
Well, because the magnets that you're using to confine inside around tokamaks, you're using semiconductors, because you can use them, semiconductor magnets.
Okay.
Maybe we should start investing more on Wi-Fi routers.
We can fuse hydrogens, become helium, but we can't make bits go over the wire. Yeah. Sorry. So you were saying about I understand fusion to create energy, understand fusion to create rockets, understand fusion to create lasers, but how will fusion help with semiconductors? Because there's only a couple of companies that can currently make semiconductors. I saw a electron microscope the other day zoom in to a microchip, and it's just unbelievable when you get to the nanoscale how many transistors they can now fit into a nanometer. So how would sort of fusion help semiconductors, do you think?
Yeah, I just realized all this time I meant superconductors instead of semiconductors. I might have gotten that right.
Okay.
Because before I was thinking about transition temperatures and then superconductivity, and then I realized I was saying all this time semiconductors. So sorry about that. Yeah, I meant superconductors. So if we get them to transition at higher temperatures, obviously it'll be easier to keep the entire reactor, all the magnets around the reactor superconducting. We can control the plasma a lot better. And then obviously, if we crack the holy grail of superconductors, which is getting them to superconduct at room temperature, well, then a lot of problems are solved, because we would lose so much less energy while transportation of electricity around the electrical grid.
Right, because I read there's 1 million tons of helium-3 on the moon, and 100 tons of helium-3, as in the byproduct of fusion, would basically power the entire planet for a year. So we don't need to bring, Starship takes 100 tons payload. Obviously, it wouldn't fit helium because of the size, but So what would you do first? Would you put your time into creating a fusion reactor, or would you start with rockets with an alternative propulsion side where you're trying to build hydrogen? What have you got a plan, or are you just going to see how it goes?
I would say if I were the government, I would put all my money into fusion, because you already have great private companies such as, you know, Musk with SpaceX improving the rocket transportation industry by themselves. So they do get contracts from the government, and they do get a little bit of help, but ultimately they're a private company and they do things their own way. Then obviously give NASA their usual budget, but put everything into fusion. And then obviously we need some resources. Obviously, I'm not saying put everything 100%, but we need some resources to finally conclude the chapter of fission energy, because although we're getting very close, we still need to conclude the development of these technologies.
Yeah. Would you look to work somewhere, Cesar, or do you want to set up your own thing? Because, you know, something like this, you could probably quite easily get funding for building a minimum viable product of a bigger reactor and do it on your own. You know, would you be interested to look at that? So
right now, I'm aiming to get degrees and a bit of work experience, work with professionals, get a lot more knowledge and expertise in the field, because although I've done countless hours of research, I still have A-level knowledge, at least for math and chemistry. And well, physics is my foundation. So I would firstly aim to get all my education done and expertise settled in. And then, yes, I was planning on doing, as you said, my own things or my own company. But I don't know if I would focus on the energy industry, because my issue, my main strength, but at the same time, my main weakness is that I like too many things. I have a lot of passions, which range from robotics to 3D printing and manufacturing and all that stuff. So I would still need to find my own way. And I definitely want to start a company. I just need the idea to start it. And I definitely enjoy working in the energy business, but I don't know if it's all I would want to do. So if I want to spend all my resources into that one, or focus also on aerospace, because ultimately, if I go to university this year, I would be doing an aerospace engineering degree. So I could possibly do that as well. But then there's always overlaps. Obviously, you can have propulsion systems with fusion and different types of propulsion systems that use similar technologies.
There's so many cool kind of side areas. I just was reading about this company that they're putting satellites into space, and they're shining huge reflectors from the sun.
Yes.
Yeah. So when you're in, you know, the sun shining in a country and it reflects to the sunlight to solar panels when it's pitch black at night, you know, they've got all these really cool technologies that are sort of coming off the side of, because look, Elon Musk is launching one spaceship a week or one a day. So it's being fulfilled, right? So to catch up with him is going to take a long time. So there's lots of other areas. I mean, bipedal robots are really taking off at the moment. So robotics is great. So out of all of those areas, you know, there's longevity, there's all these areas. Is there one specific you'd get involved in? What's your number one that you'd go for, or is it energy? Is it fusion?
Well, actually, before I answer that question, I wanted to stop on the mirror startup that I saw on the internet as well. I didn't do much research on it, but at first glance, I have a lot of questions and points to debate. Because, well, first of all, what would be the ecological impact of shining the sun in places where it shouldn't be shining at that point in time, you know? And then especially giving control to people, because I think their business model would be for people to control the sunlight with their app on their phone. And then the other thing is, how won't the mirrors be shot off their orbit? So obviously photons will have momentum, and won't they eventually start to move the mirrors out of their pre-selected and predetermined orbit?
So the way that it's going to work is they're not doing low Earth orbit, they're doing geostationary orbit. So with geostationary orbit, you pretty much can just put it on a country and it will stay there. The satellite won't move, because it effectively won't move. So what they're talking about is, I think, 1,000 satellites, each reflective mirror will reflect around a 3-mile diameter of sunlight, which is a lot. Potentially,
Yeah.
if you were going to get married, you could order in the pitch black, 3 miles of sun.
Yeah.
I think people are talking about that already. So to me, in space, obviously Maxwell's equations, in terms of EM radiation, although the intensity remains the same, or the strength of the photons remains the same, and then always the speed of light's constant, as obviously that reflects, the wavefront increases. So as those photons reach the desired location, they're going to lose strength. And obviously then you've got to go through the atmosphere, and then all of those photons are going to get reflected off of the atmosphere and within the atmosphere. So my initial gut reaction was like, how's this going to work?
Yeah.
But they've had huge investment. I mean, they're already in the billions of dollars of valuation. But I mean, it seems like a good idea. I used to run server farms back in the day, and we'd turn them on. Everybody would stop working at 5 p.m. And then from 5 p.m., all these servers are just sitting there doing nothing. If you can then allow America to use them, which are 8 hours behind, then you're doubling up and getting 50% more efficient on all of your server usage. So it kind of makes sense, but I just don't understand how those photons, once they're reflected, are going to carry the same amount of energy and intensity. Well, they'll lose a lot, even though you're 50,000 kilometers up in the air, so the sun's 100 million miles away, 150 million miles away, depending on the elliptical orbit. So to me, it's crazy. I'm not quite sure, but it's like what you're doing now. When you do these things, you learn so much, right? I think they've got their first satellite into space, so they're going to start learning a lot from it,
Yeah, I'm just skeptical because the mirror would then act like a photon sail, that was proposed propulsion method of just having this huge sail and having photons bombarded and being reflected, and you gain momentum. So unless you put thrusters on it, they eventually be slowly knocked out of their orbit and slowly move away, either gain or lose velocity. But I guess they got it sorted, or they're gonna sort it out, because otherwise, I mean, they'll have to replace that mirror every X days or months.
Yeah. I read that if you take every single telescope around the world and you record all the photons that have hit every single telescope, and you combine all those photons' energy together, it's less than 1 watt. So although they have momentum, the power's pretty small. So they're probably going to have ion thrusters. They're going to have the boats have. But yeah, there's all these other kind of, without having to create a rocket, there are all these secondary and tertiary services and products and businesses that are coming out of it, right? So, but to me, fusion's just been this kind of holy grail now for a while. It's always 30 years away. It's 30 years away. And now, if you're 17 years old and you've created this fusor, and you've actually created plasma. I saw the pink plasma. It looked awesome.
Yeah.
So you've achieved plasma. That's an awesome thing. So I just can't imagine in 10 years. I mean, do you just sit and read all night? How do you do your learning?
Yeah, most of the time when I came back from school, I just mostly learn off of YouTube, because it's the most efficient way to learn stuff, and most people explain their topics very well. Then I look at research papers that I'm forced to look at anyways, because I was doing the APQ project. So one way or another, I had to look at research papers. And then Fusor.net was my main source of information, especially because you can see what other people did and how the community reacted to those modifications and those developments. And then you can better understand what you need to do, or how to improve, or how to fix some of the problems you have. But also articles online. For example, I had to learn about the low pass and high pass filters, RC filters, to make the pressure controller unit. So I designed the electrical schematics, and then I got a matrix board, bought all the components, soldered everything together, and then I made, after 3 attempts, I made a sort of working pressure control unit that could read the pressure converted from an analog to digital signal, feed that into the Arduino, and then convert that into pressure, because the thing was the pressure gauge was giving off voltage, and you have to convert the voltage to pressure using equations and tables. So it was a very long process. I think it took me about a week or 2 weeks to develop the system to replace the control unit that previously blown up. So
okay. And I read Python and C++. What's your I've been coding for a long time, but I used to think I was good, but now looking at other people, I think I'm average. Are you a good coder, would you say?
I think that happens to everybody. I think the same thing. Whenever, especially for 3D models, there's so many good 3D artists out there. And then I do my own 3D models, and then I go on TurboSquid, which is a popular website to buy 3D models made by other people. And you look at them, I'm like, I thought I was the best in the country, and I'm not even close to these guys. So. And then you have to remember, well, these guys work, they get paid for a living to learn about digital and 3D design. They have years and years of experience and have done tons of courses. And then once you remember that, you know, everything goes back to normal. But I think we all get that sensation when looking at other people's work, especially internationally. We realize that we don't know anything.
Yeah,
that happens to me as well.
All right, and I want to ask you a question here. I mean, and it's a personal one in terms of your knowledge. Like, I'm doing my physics degree, and I'll sit down for hours and do maths equations. Again, I'm pretty average at the moment, but I can just say to ChatGPT, you know, what is, if I've got, you know, X amount of uranium-235, an X amount of, you know, and it will write out the equations. Most of them I know, but some of them I don't. And it's just done all of this and so not giving me a synopsis of, oh, you know, you need 3 grams of uranium-235 to get to the moon with a rocket. Now, before I would have had to sit down for 3 or 4 days, ask my instructor. Now I can just, are you doing that? Or do you feel like that's being lazy? Or do you think that's actually increasing your efficiency because you can ask, you know, GPT or whoever it is?
I think, well, I mainly use GPT to like correct text. So if I'm writing an email or a message, I just write my message, then feed it to GPT, it improves it, and then I send it. So that's my main use. For coding, it's also extremely useful. I mainly ask it to give me documentation. So if there's a command or a function that I don't know, I ask, can you explain this command and or function and give me some examples, and it does that. But I've used ChatGPT to create like chunks of code, not much, but I did. And I think when it comes to equations and mathematics, I really like knowing them and remembering them. It's not even, for me, it's not an argument of whether it's useful or not, because obviously it is not useful. Like if you really think about it logically, it is not useful, as you have access to the internet most of the time. And now there's ChatGPT, so one way or another, you can find the equation in 30 seconds whenever you need it, instead of remembering it. So from an efficiency point of view, it's obviously not important, but knowing the equations, at least for me, it helps me understand other topics. So if I know the equation, I know what every term does, and I remember it, then when I read a research paper or an article, I immediately understand what they're talking about. So, so yeah, ChatGPT is a useful source to prove and guide you through a problem. But when it comes to equations, I personally like to remember them and I purely understand where they're coming from with the proof and what every term means.
Okay. And in terms of, I know you're talking about with this confinement, sorry, go back to the Fusor. I know we're not really talking about temperatures, you know, that's really more for tokamaks, but do you know how hot it got inside the confinement device?
Yeah, I had another person ask me this. I never asked myself this question and calculated the temperature, but I did do an experiment where I got a piece of a chicken nugget, strapped it to the grid and placed it inside the Fusor. And when I pulled it out, it was rock solid. You couldn't see it being cooked, so it wasn't high enough to cook a chicken nugget. And then I'm guessing the effect of being very solid and strong, unlike the soft nugget that you would expect, that could also be from the fact that it was put under a vacuum, so then all the oil was evaporated and taken out. But Yeah, it's not that hot. Especially, I tried it at 5 kilovolts, and it's not that hot. Especially because you don't have that many molecules inside the chamber at that point compared to the atmosphere, and then because 5 kilovolts is not that much.
And okay, 5 minutes. And how did you? I mean, I think it's about 15 kilovolts when you can create X-rays. So there was no danger of sort of creating X-rays for you, right? No.
No, no, in that fusor, no, because most X-rays would be absorbed by the stainless steel. Then the viewport was lead shielded, so it was a glass infused with lead, so that would absorb also most of the X-rays. Then you had the camera with the 3D printer mount, and that would stop many, but it still protects you from the viewport, which, to be fair, is the point where most X-rays will get through.
One of these Geiger meters counts all the ionizing radiation.
Yeah, I still need to buy one of those. Ironically, I have the neutron detectors, but I don't have the simple Geiger counters that you could buy off of Amazon. But yeah, so as long as you, like, if you stay back a meter, I would expect very little to none X-ray radiation.
I would love to show you. I've got so many. Let me just show you something quickly. I've got. I wish I could show you some of the stuff I've got here, but this is. I brought this.
Oh, that's nice. Yeah,
it's an actual jet engine. So yeah, I've got all different types of meters here. But and I'm. I know we've only got a couple of minutes. Do you know much about electromagnetism, or are you spending your time on electrostatic, kind of the maths behind that?
Ish. I mean, I still haven't done Maxwell equations.
Okay, right. We got 2 minutes. So I just want to say, man, thank you so much, Cesar. I really appreciate it for your time. We've had an hour, and mate, you've got to keep this up. Try not to fall into, you're I don't know how to say it without, because I'm going to put this on my channel, right? You're a very handsome guy. You're young. You've got very intelligent. Try not to get swayed too much into the other side of things, because I think you can change the world, man, and that's what we need. So cheering on you and cheering on Italy, mate.
Thank you. But yeah, no, it was very nice talking to you, and I think in general, more conversations like these have to be held, and more podcasts, especially because you can publicly speak about this, and more people will listen. But it's very important to discuss these kind of topics.
A very, very cool place in the UK is the Royal Institute, and I'm a member there. I go there quite a lot. On the second floor, it's all mathematicians, and they're working on the 23 of the biggest problems, the biggest maths problems that are unsolved. You should definitely, if you're in London, let me know, and I'll take you down to meet those guys, because you'd love it there. Yeah,
I mean, next year, I had two options ish. So my first option was to either go to Turin University and do aerospace engineering. My second option was to go work at Bristol University as a tech and then reapply to Cambridge. But although I've been offered a place, unofficially offered a place at Bristol, they've taken so much time getting the contract ready, and they've been so unresponsive that it's been actually quite disappointing. So I was actually hoping that I would go to Bristol to work there, and so I could be in the UK and then go to Cambridge. But I don't know. I still have some time to get the contract up before I have to tell the university whether I'm going or not. So we'll see. I really hope I do end up there, but it's looking unlikely. But yeah, if I'm in London, I'll drop you a message.
Let me know. Yeah, and have you thought about Imperial?
I did also apply to Imperial. I got rejected last time as well as Cambridge, but yeah, I mean, yeah, Imperial is also on the table. The only thing is that if I go to another university, I cannot apply to Cambridge, because Cambridge only if you're not enrolled in any university you can apply. Yeah, and it's a very weird rule. And then if I wanted to apply to Imperial, and the fact that I only have one college on my application, it wouldn't really be worth it.
All right, Cesar, we've got 4 seconds. You're an absolute legend. Thank you very much.
Thank you.
Cheers, mate.
Good night. Cheers. Bye-bye.